Morning everyone. So today I thought that we should learn about the number systems. The number systems, like how the different data types are formed and how the different data types are calculated. So first, let me introduce you to the data types. So the most basic data types that we have are the byte, int, long, and short. So these are our first basic data types. These are also known as primitive data types in most of the languages because they only store certain values. So let's get to know like what size they are and how they actually hold the data. So for the byte, we have one byte which is equal to 8 bits, right? Let me have a table here. So let's say you have a number. Let's say you have the number data type, then their size, then their bits, the actual bits they have, size in byte and in bits. Okay, let's solve till here. Let's see. Bytes is well for byte. You have one bit and which is equals to 8 byte bits. And then for short, we have 2 bits which is equals to 16 bits. And for int, we have 4 bits. And for long, we have 8 bits. So 16, 4, 32 bits and 64 bits. So the values, the binary values are stored in the bits, not in the bytes. But the computer understands a single byte, takes a chunk of memory from bytes. So that's why we need to understand why they are stored in bytes and in bits. Well, let's take another column and say their ranges. For the ranges of byte, the range goes from -128 to 127. For short, it goes from -32,768 to +32,767. For int, a really big value, -147483648 and +214748367. So, and the long value, well, really long. I'm just going to say the max value, which is going to be 9. So you see how big the long value actually gets. So today I actually wanted to show you how these values are actually formed and how these values are actually calculated. What are the different procedures that the computer follows and how the different numbers are stored. So this was basically how different data types consume different values and how different values can store different ranges of values. So first we have the data type. Let's start small. The data type we will take is byte. So the byte holds 1 byte of value which is equals to 8 bits and it stores -128 to 127. Before that, okay, so a byte equals to 8 bits. So we know this. A byte actually holds 8 bits. Let's take again a smaller example of just 3 bits. How in 3 bits we have values that can be stored in 3 different zones. And these 3 different zones can be called as 0, 1, 2. Let's not call it that. But here we can see we have 3 positions, and in 3 positions we can store values of 0 or 1, 0 or 1, 0 or 1. So all the different possibilities that I can have, or the different combinations that I can have to store different values can be 2 to the power. Okay, let's see. So if I only had one pawn or just one bit, I can hold values which are 1, 0 and 1. For 2 bits, I can store values which are 0, 0 or 0, 1 or 1, 0 and 1, 1. So you can see, right? If I only have one cell, I can store values of 2 to the power 1, which is equals to 2 numbers. If I have 2 cells, I can store values of 2 to the power 2, which is equals to 4. And then now for 3, if I have 3, you can imagine like 0, 0, 0. Okay, I'm not going to do all of that. It will take 8 values. Okay, 2 to the power 3. 2 to the power 3, which is going to be 8 values. Actually, let's see those values and how you can store different numbers in them. So let's say these are your cells, or these are your bit positions, and you can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then again 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are all the possible different combinations that you can have with 3 different bits. Let's assign the numbers. So let's give them a serial number. And with a different serial number, we can, okay, so 0, 0, 0, we can give it a value of 0, or 0, 0, 1, 1, 2, 3, 3, 4, 5, 6, and 7. So you can see, if I just assign those values or just calculate them directly, I can store values up to 7. So for 3 bits, now we are having 8 different values. We start from 0 to 7. But we also have negative one. We also have negative numbers, right? So for those negative numbers, we need to do something. We need to split this column into halves. So again, I will consider the last bit as a splitting point. As you can see, in the half of the column, I have the last bit as 0 and then the last bit as 1. So I am splitting the table into half using the last bit. So most of you might know that the last bit is usually considered as the sign bit, right? So that's why I am cutting the column into 2 halves so that I can store negative values and positive values. The procedures that I have used here are, first, for the number of possible causes, the number of possible combinations. Number of possible combinations, which is equals to 2 to the power n, where n belongs to the number of bytes, number of bits. So that's how you can get the number of combinations. That's all. Okay, so the sign bit for storing negative values. For storing negative values, we can consider the fact that half of them are negative. Let's now just assign those values. So for values, positive will be positive, 0, 1, 2, 3, and negative, let's start with negative 1, negative 2, negative 3, negative 4. If I try to calculate a sum of positive and negative numbers, let's say negative 3 and positive 3, negative 3 plus 3 should be equals to 0, correct? But if I use those numbers directly, I will have the binary representation of negative 3 would be 1, 1, 0, and the positive representation would be 0, 1, 1. And if I try to add those, it would be 1, 0, 1, 1, 0, 0, 1. Last bit would be ignored because it overflows from the number of bits. Correct? You can see like this is not the representation of 0. Right? This is not the representation of 0. So for that, let's do some mathematics. For the negative numbers, we have another procedure. For negative numbers, let's say we have a number x and x is less than 0. So for x, I can have its complement. So the complement of x, then I will add 1 to it. Okay, let's see why we are adding. If I am just flipping this table, I will have values like, if I flip the table, I will have values like negative 0, negative 1, negative 2 and negative 3. But there is no such number as a negative 0. 0 is neutral. So that's why I am adding plus 1. So negative 1 plus 1. Sorry, first I am complementing them and then adding 1. So the numbers will be shifted at top. So now you will be getting values. I will not be using 0 in this situation. So I will have only 1 0, which is represented by 0 0 0. Correct? So our original assumption was the numbers were simply minus of their number. So again here, a procedure I will follow, which is complementing a value, and adding 1 to it. And let's take an example of 2. I have 2 which is represented using 0, 1 and 0. So first for complementing, the bitwise operator, which is a tilde, the not operator will be used, and the not operator will perform the calculation of flipping the bytes, flipping the bits, which will be 1, 0, 1. So you can see that 0 can be converted to 1, 1 can be converted to 0. And then I am going to add it. I am going to add 1 to it. So with adding 1, I will be getting a result of 1, 1, 0. Correct? So according to this, our new assumptions 1, 1, 0, 1, 1, 0. This should be our negative 2. And again, now we are flipping. Now we are performing the not operator, flipping the table. So our numbers will start from below. So this will be considered as a negative 1, then the negative 2, now we have seen, then this will be considered as a negative 3, and this as negative 4. So we have performed calculation only if the number is less than 0. So these are all the numbers which are less than 0. And for the positive numbers, they will stay the same, 0, 1, 2 and 3. Okay, so this is our negative number calculation. Let's see if it works. We have done it for 2. Let's check it for 2. So we have the example. So we have the example of negative 2. Okay, 2 minus 2, which can be written as 2 plus negative 2. Correct? And from this table, we can just look up the values of 2 and negative 2. So here the 2 value will be 0, 0, 1, and the negative 2 value will be 1, 1, 0. Correct? So if I add these values, negative 0 and 2 is 0, 0, 1. Sorry. The 2 value is 0, 1, 0, and the negative value is 1, 1, 0. So if I add these two values, I will be getting 0, 0, 0, 1 plus 1, 1, 0. So 0 and the 1 carry, 1 plus 1, 0, 1. So the last bit will be discarded because you only have 3 bits to store the values. So you can see we are getting 0, and negative 2 plus 2 is equals to 0. Correct? So this is how the numbers can be stored in a 3-bit system. So we have only looked at 3-bit system. But now we know the possible number of combinations that the value that the number of bits can hold. For 3-bit can be 2 to the power n, where n denotes the number of bits. So 2 to the power n, we can hold up to 8 values: 0, 1, 2, 3, 4, 5, 6, 7. So these are the 8 values that a 3-bit can hold. And for the negative number calculation, which are for the numbers which are less than 0, we need to perform this procedure. So this is how you can store values of negatives. This is how the computer stores the value of negatives. But let's see. We were originally talking about bits, bytes, int, long, short, right? So now you know how a number is calculated. Let's see how those ranges are derived. In the ranges, how bit represent the number of memory slots, and a byte, the byte data type, holds 8 bits or 1 byte of value. Let's calculate it for those without using this table or such a mess. Okay. Before erasing the table, I should have derived the range, right? So our original 3-bit system, the 3-bit system could hold values of 0, 1, 2, and 3, right? And in the negative scenario, it could hold a value of negative 1, negative 2, negative 3, and negative 4. So it could hold the 8 values, and the ranges that we can write is the number of 2 to the power n, which is equals to 2 to the power 3, which implies 8. So we have 8 values that we can hold, and the ranges we can possibly assume for the max range or for the max value, it is half of this, because originally we took the sign bit as the last bit, and the last bit only follows the half of the table, right? For the max value, it would be half of this. It would be half of this, which is 8 half is 4. Or let's say this 2 to the power n divided by 2, which is equals to 2 to the power n minus 1. So that would be 2 to the power 2, which is equals to 4. Okay, sorry, the max value is 2 to the power n minus 1 minus 1. Which again denotes 2 to the power n minus 1, 2 to the power 3 minus 1, 2 to the power 2 minus 1, which is equals to 4 minus 1, which is equals to 3. So this is our max value for a 3-bit number system, right? And then the min value, okay, let me write the procedure for the max value. For the max value, I got procedure of 2 to the power n minus 1. Correct? And for the min value, again the sign bit we have actually half, so we will be using the same formula, 2 to the power n minus 1. But here 2 to the power n minus 1, in this case 2 to the power 2, 4, that was our negative value. So we need to understand that for negative values the sign bit must be flipped, and the computer interprets the last sign bit as the negative sign whenever it represents the number, right? And then for the min value, we will be using the procedure 2 to the power n minus 1. So here the n was 3, which implies 2 to the power 3 minus 1 is equal to 2 to the power 2, which equals to 4. But the 4 will be represented. This is just for our understanding, but the 4 will be represented in negative values with a negative sign. So this can derive us the min value for any number system, whatever bytes it may use or whatever bits it may use. So for min value, we got the formula of 2 to the power n. minus 1. If you want to show it to a user or show it to a human, then we need to have a symbol of negative 1. So let's first derive the value of a byte. What are the min value and the max value? Byte originally hold 8 bits, and so 1 bit was for sign, that's why the negative 1 in the max value, and the min value it doesn't uses 0, so negative 1 plus 1 which becomes 2 to the power n. Okay, so a byte which uses 8 bits of memory, correct? So the number of possible combinations will be 2 to the power n. So here 2 remains the same, n remains the number of bits, 2 to the power n, which equals to, let's see, 0, 5, 6, 7. So 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 32, 64, 128. Again, now we have 8 bits, right? So for 8 it will be 256. So the possible number of combinations that a byte can hold is 256. You can represent 256 number using 8 bits. Alright. So these are the possible numbers that it can show. Possible numbers it can represent. And with the possible number of combinations, let's calculate the value for the max value. The max value uses the formula of 2 to the power n minus 1. So here 2 remains the same, n means the number of bits. Yes, 2 to the power n minus 1. Min value also remains the same, 2 to the power n minus 1, because we are halving the number of possible combinations. If we had 2 to the power n, then it will be 256, but we have divided the table or split the table with the last sign bit as 0 and 1. Right? So with the formula 2 to the power n minus 1, which is 8 minus 1 equals to 2 to the power 8 minus 1 is 7. 7 minus 1, which is equals to 128 minus 1, and that equals to 127. So you can see the max value from the original table. If you calculate, if you go through your previous notes, you will see the max value was actually 127. And again, for the min value, we came to the conclusion that min value can be represented by 2 to the power n minus 1 into negative 1 for human representation of this negative sign. Right? It will be 2 to the power n minus 1 and is 0 of 8. 2 to the power n minus 1 into negative 1. Right? 2 to the power 8 minus 1 into negative 1. Well, 2 to the power 7, well 7 was 128. 2 to the power 7 minus 1, which is equals to 128. Negative into negative 1, which comes to negative 128. So here you can see how a byte with 8 bits can represent values up to 127 and in negative ranges up to 128. So like that, I want you to perform this calculation, and I want you to see how the int, short and byte values, int, short and long values can be formed. Well, for long the number actually goes into 9 quintillion, so you don't have to do that. Also for the int, which goes into 2 billion, so you must try for the short. Right? I hope you understood today's topic. That's all. I wanted to show this representation because it was missing from the lecture, and I thought that the students should really know this, like how the numbers are calculated and how the different bits and bytes can store the values, how the computer understands these values. So that's what's called IE. Thank you for listening.